Okay, we wanted some answers to a quiz questions, and here they are. Here's a quiz question first. What is the hybridization of carbon in C2H2? And so hopefully you recognize that C2H2 is ethylene or acetylene, but if you don't, you would count up the number of valence electrons. 2 times 4 plus 2 times 1 gives us 8 plus 2 is 10 valence electrons. You connect the carbons to each other, and then each carbon gets one hydrogen, and that uses 2, 4, 6 electrons. So you could put a couple on each carbon like this, but then each carbon has only 6 electrons in its environment, so it's going to force its neighbor to share. So you have this guy shares over here, and this guy shares over here, and so you end up with the carbon-carbon triple bond. And so once you get a good Lewis structure, you can answer the question about hybridization by counting the number of electron domains in the carbon. So this carbon is attached to a carbon and a hydrogen, so that's 2 electron domains with no lone pairs. So 2 electron domains equals linear in terms of geometry, and then that means sp hybridization. So this hybridization of carbon in C2H2 is sp based on this dot structure that I drew. Now, what is the formal charge in oxygen in the Lewis dot structure of carbon monoxide that has a triple bond? And formal charge is a special accounting method to try to predict charge distribution. It's not the same as a real charge. So carbon monoxide, 4 plus 6 equals 10 electrons as well. If we attach the carbon to the oxygen would prefer to have more electrons because it's more electronegative. So I'll go ahead and put 6 electrons around that to fill its octet. 2, 4, 6, 8. I still have a pair to put on the carbon. And then this carbon only has 4 electrons in its environment. So we need to pitch 4 more into there. Good old organic electron arrow pushing. We're going to make lone pairs turn into bonding pairs. And if we do that twice, we will get a nice dot structure for carbon monoxide where the octets are filled for all atoms. And our reference is a neutral carbon would have 4 electrons in its environment, or not in its environment, it would be assigned 4 electrons, 4 valence electrons. A neutral oxygen would be assigned 6 valence electrons. This carbon obeys the octet rule by having 8 electrons in its environment, but the number that it owns is it has these 2 all to itself, plus it gets 1 electron from each of the shared pairs. So the shared pair of electrons gets distributed 1 to each atom that's sharing, nice and even, no greed there. And so this carbon, we assign 1, 2, 3, 4, 5 electrons to it. So that would give it a minus formal charge, because carbon would have 4 valence electrons if it's neutral. We assign it 5 here. The oxygen, we also assign 1, 2, 3, 4, 5 electrons. It would be neutral with 6 electrons, so its formal charge is plus 1. And what that predicts is that the carbon will pull more electrons to itself than you would expect based on other factors. So electronegativity would predict that the oxygen is more negative, but the formal charges predict that the carbon is more negative. And since those guys are competing, it actually describes the real case pretty well, that there's not a lot of bond dipole in carbon monoxide. Because carbon is trying to fill its octet, it makes it behave as if it's more electronegative. But in any case, the formal charge on oxygen is plus 1, in this particular dot structure. And I indicated the dot structure where carbon monoxide has a triple bond because if people are trying to minimize formal charges, they'll actually draw this dot structure which has no formal charges. But the one that the question asks about is the resonance form with the triple bond, which has the unattractive formal charges because the less electronegative element is pulling more electrons, it looks like. Alright, so a lot of elaboration on that one. Electron domain geometry about nitrogen and N2H2. And like all these questions rely on good dot structures. So this is essentially a boot camp for dot structures. 2 nitrogens, 2 times 5, 10 electrons, 2 times hydrogen, 2 times 1, gives us 12 electrons for this structure. Connect the nitrogens to each other, and each nitrogen gets a hydrogen. And then we put in, we have 2, 4, 6 electrons. So, put in 6 more, and that's enough to fill the octet of this guy. So 8 electrons in his environment. But this guy has only 6 electrons in his environment, so he's going to force him to share, and that's going to give us a nitrogen-nitrogen double bond, and each nitrogen has a lone pair of electrons and a hydrogen. So now this, I've drawn this as if it's linear, but it's not really, because this nitrogen has 2 atoms attached to it and a lone pair, so 3 electron domains, which means it's a trigonal planar electron domain geometry. And that's what the question asks for. The electron domain geometry about that nitrogen is trigonal planar. The hybridization here is sp2, and this is going to look bent. The nitrogen-nitrogen-hydrogen angle is going to be probably close to 120 degrees, maybe 117. If we wanted to draw a better representation of that, we would draw it more like this, where you can see the trigonal planar electron domain geometry, where the lone pair is pushing the 2 atoms away from each other, or actually towards each other. The lone pair is going to push these 2 atoms towards each other, making a bent structure rather than a linear structure. So there we go, electron domain geometry, trigonal planar, with a little more elaboration there as well. Quite a busy little quiz here. Now, these next 2 questions are about the CH3 minus ion. So again, dot structure would be critical. 4 valence electrons for the carbon. 3 for each hydrogen would be 7. But then we also have to add in 1 electron due to the minus charge. So 4, 7, 8 electrons here. Carbon attaches to 3 hydrogens. That uses 6 electrons. So we have a lone pair to fill the octet of the carbon. CH3 minus. And here we've got 2 questions, really sort of out of order, that I need to think of the electron domain geometry first to visualize that. And so the electron domain geometry, we have 1, 2, 3, 4 electron domains. So that's going to give us a tetrahedral electron domain geometry. The 3 atoms and the lone pair, tetrahedral electron domain geometry. And that makes this carbon sp3 hybridized. This bond angle is going to be a little less than 109.5 degrees. The lone pair pushing things a little closer together than the ideal 109.5 degree angle. And when you go to the shape, it's So back up to question number 4. When you're talking about the shape, you got to realize the lone pair is invisible. So just the arrangement of the atoms, based on how they're configured in the electron domain geometry, now we visualize just the atoms, and we see that this is trigonal pyramidal. So there we go. There is an invisible lone pair that constitutes part of the electron domain geometry. So electron domain geometry, we pretend we could see the lone pair and describe the shape. For the actual shape, we realize we can see the atoms, and we describe the arrangement of the atoms as trigonal pyramidal. So there we go, little quiz. I hope everybody dominated, and anything that you might have gotten wrong or need a little help with, I hope this quiz is instructive.